Hello everybody, I am presenting this video as a part of my final project for the Wireless Communication course under Professor Wu at the University of Florida. The topic for presentation is study of OFDM technology and its performance analysis in terms of BER or the bit error rate. I will try to keep the explanation simple and understandable in layman's terms. So the agenda for today. First, I'll start with introduction, followed by the understanding of the basic concept of OFDM transceiver system, OFDM water filling algorithm, BER analysis for various channel models, estimation and analysis of carrier frequency offset, estimation and analysis of STO or symbol time offset, conclusion, and finally a MATLAB demo. So introduction. Orthogonal frequency division multiplexing or OFDM is being widely used in a number of communication applications today because of its ability to support very high data rate. What is the need for multi-carrier system? Multi-carrier system has gained its importance because of its ability to reduce the failure rate, fading effects and ISI that a single channel subcarrier system suffers from. So what happens in a single carrier subsystem? So if one channel fails, the entire system fails. However, in case of multi-carrier system, the bandwidth is divided into a number of subbands and the failure of one subband does not impact the entire system. Like any other transceiver system, OFDM suffers from few of the caveats, like it suffers from intersymbol interference, intercarrier interference, phase shift, and if it is not taken care of, there can be signal distortion at the receiver side. It also suffers from carrier frequency offset and symbol time offset. So basically, we should take care of this while designing our transceiver system. So for the optimal design of this systems, performance analysis of OFDM under various channel conditions and under the impact of receiver offsets needs to be carried out. Here, there are two fading channels, namely AWGN and Raleigh, has been taken into consideration. OFDM is widely used in 3G, 4G, LTE, wireless networks, WiMAX, audio, video, digital broadcasting, etc. Next, design analysis of OFDM system. OFDM technology is based on multi-carrier modulation, and to have a better understanding of this technology, I will first discuss the advantages of multi-carrier modulation over single carrier. The demand for high data rate transmission increased the need for higher bandwidth. However, with the increase of bandwidth will result in the increase in probability of ISI due to multipath fading. To nullify this effect, adaptive equalizers are used. Thus, with the increase in bandwidth, the design of the equalizers become more and more complex. Multiple carrier can be used for the transmission of high data rate. In a multi-carrier system, the wideband is subdivided into n channels and each channel is assigned a frequency. So, orthogonality among the channels can be maintained to avoid inter-carrier interference. This reduces the complexity in the design of the equalizers. OFDM and FMT are two multi-carrier systems that can be used. However, FMT requires filter. So this makes the design of FMT more complex than OFDM. So OFDM technology gained popularity in transmission of high data rate symbols. Next, the subcarriers of OFDM scheme might follow any of the modulation techniques like AM, FM, BPSK, QPSK, QAM, and so on. So what is the need for orthogonality among the subcarriers? To increase the spectral efficiency of the channel and reduce the intercarrier interference, orthogonality is a must. The subcarriers are generally sine and cosine waves, and to maintain the orthogonality between the subcarriers, a harmonic relationship between the frequency of the subcarriers is maintained, which can be shown as e to the power j 2 pi k n, where k can vary from 0 to n minus 1 and so on. Modulation and demodulation of OFDM with local oscillators. For OFDM modulation, the input data is first converted into n parallel data with the help of serial to parallel converters. Let me take you to the next slide, which has the pictorial block diagram of it. So we first see that there is a serial to parallel converter. These parallel data are then modulated with the help of n carrier frequencies which are orthogonal to each other, and these are the local oscillators. So after modulation, all the n signals are added together and this forms the passband signal ST, which are then transmitted over the channel using antennas and power amplifiers. We see that there also it suffers from distortion, and here the actually transmitted signal becomes S-T. So the demodulation technique is generally just the inverse of the modulation technique. So the demodulation technique first involves the down conversion to form the baseband signal, and from there we use a low pass filter. The subcarriers for each subband are then derived, and finally it is fed to a parallel to serial conversion for parallel to serial conversion using a PS converter. Next is the replacement of local oscillator with FFT and IFFT. So the output derived from IDFT block are orthogonal and can eliminate the local oscillators. Thus, it helps in overcoming the complexity that arises due to the use of local oscillators. Also, instead of using IDFT, IFFT can be used for reducing the complexity of the computation and for performance optimization. In the block diagram shown below, we see that local oscillators are replaced by IFFT blocks at the transmitter side and FFT block at the receiver side. CT is a transmitted OFDM signal and RT is a received signal impacted by various channel impairments. The constellation mapper block is basically the modulation technique that is employed on the given signal like QPSK, CAM, QAM or BPSK or whatever. So now, what is this addition of cyclic prefix and removal or deletion of cyclic prefix? What are these blocks about? This will be our next topic of discussion. So, the need for guard band in OFDM. What is ISI or intersymbol interference? Intersymbol interference occurs due to the interference of the previous and the current signal due to the delay at the receiver end due to channel impulse response or multipath fading. The increase in symbol period results in the increase of the length of the OFDM symbol, and it becomes larger than the time span of the channel, which results in the corruption of the first few beats in each sample. So, guard intervals are inserted between two symbols. These guard intervals can be of type 0 padding, addition of cyclic prefix, or cyclic suffix. By properly selecting the length of the guard interval, intersymbol interference can be avoided. At the receiver side, this guard interval data is discarded, and so as they do not contain any signal information. Addition of cyclic prefix or cyclic suffix helps in removing both the intersymbol and intercarrier interference. So they are used in practical systems. The only demerit of guard band is that guard band decreases the symbol rate because of the increase in symbol length. This slide contains the pictorial explanation of guard band. Figure 5 shows the intersymbol interference. Figure 6 shows how guard band can prevent intersymbol interference. Figure 7 shows the addition of cyclic prefix. The last few bits of the symbol are added to the front of the symbol, which is TG. So now the new symbol length becomes TSym equal to T sub plus TG. So there is an increase in the symbol length by TG, which is the guard length. Next is the optimal power allocation by following the water filling algorithm for OFDM system. Water filling algorithm sounds interesting, so what it is? The basic principle of water filling algorithm is that more amount of power is and more number of bits are allocated to the channels having higher signal to noise ratio and lesser power is allocated to channels having low signal to noise ratio. This will help to enhance the utilization of bandwidth for the entire system. This technique is applied in cognitive radio as cognitive radio is based on the concept of optimal allocation of power. The mathematical equation for this is shown in the slide. So it's saying that if 1 by lambda minus NSR is less than or equal to 0, then no power is allocated for that particular subchannel or the subcarrier. This algorithm increases the system complexity as it requires a feedback path for passing this channel information between the transmitter and the receiver. And also the approach is quite complex as in modern environment the channel varies across time. So here goes the pictorial representation of water filling algorithm. So here the height of the water is given by 1 by lambda and the NSR is the bottom of the tank. So it clearly indicates that the channels having higher noise to signal ratio are allocated lesser amount of power, and if they are above a particular threshold then they are allocated absolutely no power. For example, the first bar in the figure 8 here, no power is allocated because of the noise here is much higher. Figure 9 is a MATLAB simulation of water filling algorithm done as a part of this project. BER analysis of OFDM under various channel conditions. Wireless signals are prone to loss of data and fading. This makes it important to analyze the modulation scheme with various channel models. However, no channel model is a perfect real-time model. The better selection of a fading channels helps in better designing of a transceiver system. Bit error rate analysis of OFDM signals for various channel models give us a fair idea of the performance of OFDM-based modulation scheme. In this paper, performance analysis has been done by evaluating the MATLAB plot for OFDM for the two most popular channel models known, the additive white Gaussian noise channel and the Rayleigh fading channel model. In the Rayleigh channel, Rayleigh model can be used to understand the signal that faces fading due to multipath obstruction due to the urban environment and also from the layer of atmosphere like the troposphere and the ionosphere. This can be used to study the cases when the transmitter and receiver are beyond the line of sight. And generally this is a practical, this can be considered as a real-time channel because in most cases the transmitter and the receiver are not in line of sight. Additive white Gaussian noise channel are more idealistic channels as uh, they only add some white noise to the signal and it does not consider the multipath fading that that a signal faces in real-time scenarios. So what is next we will discuss what is bit error rate and signal to noise ratio. So bit error rate is a very important parameter that determines the quality of a communication on a radio channel. Higher bit error rate results in more data loss, delay at the receiver side, and decrease in throughput. So bit error rate is the number of bits that are in error from among the transmitted bits. Signal to noise ratio can be defined as the ratio of the energy per bit to the noise in 1 Hz of bandwidth given by N0. So BER and SNR are inversely related to each other. That is, more the signal to noise ratio, higher is the signal to noise ratio, lesser is the bit error rate. So plot for OFDM signals under various channel conditions. Here first, we will analyze the scenario with guard band. Figure 11 and 12 shows that the inclusion of guard band improves the bit error rate for Rayleigh fading channel. If we analyze this graph, we can find out that when the SNR is 15, the BR of the guard channel, BR of guard length 16, if the SNR is 15 here, in this case, the bit error rate is below 10 to the power minus 2, whereas in this case the BER is higher than 10 to the power minus 2. That means in figure 12, which has a guard length, the bit error rate is lesser compared to the bit error rate in figure 11. So with the inclusion of guard length, the performance of an OFDM system increases. Next, plot for OFDM signal under various channel conditions. Here we have taken two different modulation techniques, QPSK and 16QAM or 16QAM. For figure 12 and 13, we can conclude that the performance for a system which employs QPSK is better than a 16QAM system. Therefore, we can conclude that the type of modulation of the constellation mapper and the guard length impacts the BER of an OFDM. The inclusion of guard band reduces the ISI and therefore improves the performance of the system. Next, cause and effect of CFO in OFDM. CFO or carrier frequency offset arises due to Doppler shift and occurs due to the carrier signals in the OFDM modulation. Doppler frequency shift arises due to the change in frequency when a signal passes through a medium. The frequency offset is a difference in frequency between the transmitter and the receiver. In case of OFDM, the subcarriers with higher frequency are more prone to CFO than the ones with lesser frequency. The integer frequency offset increases the bit error rate, resulting in the degradation of the performance. In case of fractional frequency offset, the frequency is shifted by fractional part, which results in the loss of the orthogonality of the signal, which further results in the ICI or the intercarrier interference. So bit error rate of OFDM in presence of CFO. So the pink line here has more CFO and therefore it has higher bit error rate compared to the red line here, which has lesser CFO. CFO estimation techniques. Next, it is necessary to understand as to how to estimate the CFO that causes distortion in the transmitted OFDM symbols so that its effect can be compensated at the receiver side. CFO can be estimated in two domains, namely the time domain and the frequency domain. Two ways to do the time domain estimation are the cyclic prefix method and the training symbol method. Cyclic prefix method based method are preferable for fractional frequency offset but cannot deal with integer frequency offset. Training symbol method or the Moose method is better than CFO, but it's mathematically proven that it increases the mean square error. Frequency time-based technique or the Klassen method introduces some pilot symbols to track the CFO. It's better than time-based estimation techniques. This estimation techniques consist of two modes, the acquisition mode and the tracking mode. The CFO is first estimated in frequency domain and then it is compensated in the time domain. So here comes the performance for various CFO techniques. The CP based technique is worst in terms of mean square error compared to Moose, and Klassen based method, which is a frequency based method, is the best of all the three techniques shown here. Cause and effect of STO in OFDM. So here there are four cases. The first case is the idle case where there is no interference or phase shift. Starting point of the OFDM symbol is the same as the exact point of the symbol should have started. Thus, the subcarriers are orthogonal and there is no ISI. In case 2, the starting point of the OFDM symbol is ahead of the position of the exact start point position should have been. But it is after tau max, that is after the previous OFDM symbol that has lagged because of the impulse response of the symbol. This results in phase shift, but the orthogonality of the symbol is preserved. In case 3, the starting point of OFDM is before tau max. This destroys the orthogonal nature of the subchannels. Also, it suffers from inter-symbol interference and ICI. Case 4 results in both ISI and phase shift, and the effect of STO is more complex and more severe under this circumstances, and thus the distortion of the received signal is more. In this case, the start point of the symbol is just after the exact starting point. This results in the destruction of the orthogonality of the subcarriers. Time-based estimation techniques for STO. STO results in phase shift and inter-symbol interference. So it has both the time-based and frequency-based technique. But in this project, I have basically concentrated on the cyclic prefix-based method, which is a time-based estimation technique. So cyclic prefix-based technique is based on sliding windows, and these windows can slide to find the similarities between the samples, and the similarities between them is maximized when the difference between them is minimized. Another technique to nullify STO is the maximum correlation technique. In this technique, the correlation between W1 and W2, the sliding windows, can be applied to reduce the effect of STO. So estimation of STO. The plot in blue represents the STO estimation by maximum correlation method, and the plot in red represents the STO estimation by minimum difference method. Similarly, the blue dot represents the STO estimated by maximum correlation method, and the red dot represents the STO by the minimum difference method. So before going to the conclusion, I'll just quickly give a MATLAB demo. So this is the OFDM water filling model. So here goes. We see that like in the first bar, since the noise to signal ratio is less, more power is allocated compared to this where the noise to signal ratio is so high that no power is allocated for this particular channel. Next, effect of carrier offset on OFDM system simulation under additive white Gaussian noise. This needs a little time to simulate. Okay, so here goes. The line in pink here is affected by carrier frequency offset the most. So the bit error rate in this case is high. And from here, the CFO is lesser. And for the red, it is the least. So the bit error rate is less here. Next goes the CFO estimation by the various techniques we have already discussed. So this is the CP based technique, and here the mean square error is higher compared to the Klassen based technique, and this is the Moose based technique. So frequency based technique, which is the Klassen based technique, is the best among all the three. Next, coming to the STO estimation. So here I have done a performance analysis of STO estimation with minimum difference and maximum correlation based estimation methods, which I have already discussed in my slides. And here the values of STO is -3, CFO is 0, STO is -3, CFO is 0.5. Here STO is 2 and CFO is 0, and for here it's 2 and CFO is 0.5. So these were my MATLAB simulations. Now coming back to the conclusion. So why so OFDM is widely used in today's high-speed communication system, which demands higher data rate transmission and is also the future of wireless communication system. Also, the replacement of oscillators with fast FFT blocks and IFT blocks, and the development in semiconductor industry, which facilitated the design of FFT blocks and IFT blocks simpler, has resulted in the popularity of in OFDM getting popularity. In this project, the main focus was on the design of OFDM transceiver system together with the BER analysis under various channel conditions and the CFO and STO, or the carrier frequency offset and symbol time offset estimation. So this is the end of my presentation. Thank you. Thank you.